Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the previous lecture, which is a part of the phase transformation. In phase transformation, we will continue with our previous topic, kinetics of phase transformation, which we discussed which we have introduced only the kinetics of phase transformation. With the phase transformation, normally at least one phase is formed that has different physical or chemical characteristics than which have different structure. Maybe the structure may also be different than the parent phase. Furthermore, most phase transformations do not occur instantaneously. Rather, they begin by the formation of numerous small particles of new phases, which increase in size until transformation has reached completion. The progress of phase transformation may be broken down into two distinct stages: nucleation, and growth. Nucleation and growth mechanism. The progress of phase transformation may be broken down into two distinct stages: nucleation and growth. Nucleation involves the appearance of very small particles or nuclei of the new phase, often consisting of only a few hundred atoms, which are capable of growing. During the growth stage, these nuclei increases in size, which results in the disappearance of small or all of the parent phase. Like we have already discussed, that the parent phase properties is different from the new product. So the transformation of one phase to another phase, like we can further explain with the example, like in iron carbide diagram, if some portion of carbon at 0.76% carbon is added to the austenite region, then cementite and small ferrite alpha particles are formed. This reaction is also studied previously in iron carbide diagram, in which the phase, the properties of the structural properties, physical and chemical properties are different from the austenite region. Cementite region properties are different than austenite region. The transformation reaches completion if the growth of these new phase particles is allowed to proceed until equilibrium friction is attained. Mechanics of nucleation is continued. There are two types of nucleation: homogeneous and heterogeneous. We have discussed this in types of classification of transformation: homogeneous and heterogeneous. These are the two types of nucleation. The distinction between the homogeneous and heterogeneous is made according to the site at which nucleating events occur. For the homogeneous type, nuclei of new phase form uniformly throughout the parent phase. Also, it depends upon the types of cooling, like supercooling, and the temperature range as well. For the heterogeneous type, nuclei form differently. Its structural inhomogeneities, such as the container surfaces, insoluble impurities, grain boundaries, and dislocations, and so on. The further, if we add with a homogeneous type over here, the homogeneous homogeneous type of solution. The homogeneous type of nucleation is nuclei form uniformly throughout the parent phase. It requires considerable supercooling, starting from the range of 800 degrees centigrade to 800 degrees centigrade to 300 degrees centigrade. The supercooling range. One main difference. For the heterogeneous type, the supercooling is very small, like 0.1 to 10 degrees centigrade, the temperature range. So it forms heterogeneous nucleation form. Its structure in homogeneities, container surfaces, insoluble impurities, grain boundaries, and dislocations. Here we begin by discussing homogeneous nucleation because its description and theory are simpler to treat, and later on we will discuss the heterogeneous type. The principles are then extended to discussion of the heterogeneous type. Maybe we will discuss in the next lecture, but first we will discuss the mechanism of nucleation formation for the homogeneous type. Mechanics of nucleation for homogeneous type. The theory of nucleation involves one parameter. We call it Gibbs free energy. Free energy. In brief, free energy is a fraction of other thermodynamic parameters, of which one is the internal energy of the system. We call it enthalpy. The other thermodynamic parameters, one is the enthalpy. Usually in thermodynamics we were representing enthalpy by H. The other parameter is enthalpy H. And another measurement, another is the measurement of the randomness or disorderness of the atoms or molecules. So the theory of nucleation involves thermodynamic parameter called free energy. We call it Gibbs free energy, G. This free energy is a function of other thermodynamic parameters. Like one is enthalpy. What is enthalpy? Enthalpy, the measurement of the internal energy of the system, is the measurement of the internal energy of the system. The other is measurement of the randomness or disorderness of atoms or molecules. We call it entropy. Entropy is represented by S. Enthalpy and entropy. Free energy is a function of other thermodynamic parameters. Other thermodynamic parameters are H and S, enthalpy and entropy. Relative to phase transformations, an important thermodynamic parameter is the change in free energy. Wherever we studied about the change in free energy, we represent by delta G. Over here delta is missing. Change in free energy, delta G. Delta G, a transformation will occur in change of internal energy. A transformation will occur spontaneously only when delta G has negative value. For the sake of simplicity, let's first consider a solidification of pure material, assuming that nuclei of solid phase form in the interior of the liquid is in the solid phase. As atoms cluster together so as to form packaging arrangement similar to that found in the solid phase. We will discuss the formation of nucleation with this example. Initially, for the growth, the nucleation formation, one solid nucleus is formed, surrounded by the liquid molecules. Later on, some other molecules, the formation of other molecules begins, nucleation molecules begins to form, and the other solid, the liquid phase begins to solidify, surrounded by some other nucleation. And then after that, crystal molecules are increasing, and then the crystal growth stops once it reaches the equilibrium. It is assumed that each nucleus is spherical and has radius r. Over here we have discussed a simple, we have assumed a nucleus. In this figure we have explained a nucleus for a circular. This circle represents a nucleus. It is assumed that it has a radius r, and the volume of that spherical molecule is 4 by 3 pi r cube. It's uniform. It is assumed that it is uniform. The area is 4 pi r square. This is the solid liquid interface boundary. Inside that it is a solid which is surrounded by a liquid. There are two contributions to the total free energy that accompany solidification transformation. The first is the free energy difference between the solid and liquid phases, or the volume free energy delta GV. We will explain the volume free energy with some equations. Delta GV. Total free energy. Let's reconsider the total free energy. Total change in free energy. Internal energy G, or delta G, change in internal energy. There are two contributions to the total free, the change in total free energy which accompany solidification and transformation. The first is the free energy difference between the solid and liquid phases, or the volume free energy delta GV. Its value will be negative if the temperature is below the equilibrium solidification temperature. The magnitude of its contribution is the product of delta GV and the volume of the spherical nucleus 4 by 3 pi r cube. When we write the magnitude, it will be 4 by 3 pi r cube multiplied by G delta G V. The second energy contribution is, this results from the formation of the solid liquid phase boundary during the solidification transformation. Associated with this boundary is a surface free energy gamma. Surface free energy is another parameter, we call it gamma. With this boundary, the second energy contribution results from the formation of solid liquid phase boundary. The solid liquid phase boundary, like nucleation, formation was a circle with radius r. This is a solid, this is surrounded by liquid. Over here this boundary is a solid liquid boundary. Associated with this boundary is a surface free energy. Over here, surface free energy gamma, which is positive. The magnitude of this contribution is the product of delta GV and the volume of the spherical nucleus. Product of delta G V. The magnitude of this contribution is the product of delta GV and the surface area of the nucleus. Surface area of the nucleus is 4 pi r square. Finally, we combine the first contribution and the second contribution is a total free energy. The total free energy change is equal to the sum of these two contributions, that is total free energy change for a solidification transformation. Delta G is 4 by 3 pi r cube times delta G plus 4 pi r square times gamma. Gamma is the surface free energy which is associated. This term is associated with the solidification transformation, solid liquid phase boundary. This term is associated with the nucleus formation surrounded by the solid liquid boundary. So the total free energy is the sum of the two contributions. This is the first contribution, this is the second contribution, second energy contribution. These are two types of energy contributions. So when you are asked about to find out the relationship of the total free energy change for the solidification transformation, this is the equation. Delta G is the internal energy or the total energy for the solidification transformation. Here we explain the previous equation, the two contributions equations with this schematic curves. These are the schematic curves for the A is the figure A 10.2a is schematic curves for volume free energy and surface free energy contributions to the total energy change attending the formation of spherical embryo nucleus. For the don't confuse with embryo and nucleus, these are the same during solidification. Schematic plot of free energy versus nucleus radius, on which is shown in the critical energy change delta G and the critical nucleus R. So this volume, surface and total free energy contributions are plotted schematically in these figures. In figure 10.2a, this one, it is noted that for the curve corresponding to the first term, or for the equation of 4 by 3 pi r cube delta GV, for this equation, this is the curve for the first term 4 by 3 pi r cube delta GV. The second term is 4 pi r square gamma. This is the second term energy. Over here this term is negative 4 by 3 pi r cube, while this term is positive. Horizontally the plot is for the radius and free energy. Vertically the free energy delta G is plotted. The curve resulting from the second term is the equation for the 4 pi r cube. This equation actually we call it equation 10.1. The energy values are positive and increases with the square of the radius. Over here r square. Uh, while over here the energy values are negative and the increases with the cube of the r. The curve associated with the sum of the both terms is 10.2b with both terms. The curve, this is the curve associated with both terms when both terms are combined. These are the curves associated over here in the 10.2b. The dotted curves are the individual constituents contribution 4 by 3 pi r square. Over here this is pi r square gamma. Over here this one is the 4 by 3 pi r cube delta gv. The green line is the combination of the two plots. In a physical sense, this means that as solid particles begin to form as atoms in the liquid cluster together, its free energy first increases. If we look at from 0, free energy first increases until it reaches a critical radius r steric. R steric is the critical radius for which the maximum energy is required. So, and the free energy first increases at maximum. If this cluster reaches a size corresponding to the cluster radius r steric over here, then the growth will continue with the accompaniment of a decrease in its energy. Over here, if we look at the after this delta g, the energy, the horizontal is delta g steric, r steric. If we look at the r steric, the internal energy decreases until it reaches over here 0, and then the energy is negative. This subcritical particle is embryo, whereas the particle of the radius greater than r steric is termed as nucleus. The particle greater than r steric over here is embryo, less than r steric is embryo, greater than r steric is nucleus. A critical free energy delta G steric, which is shown over here, occurs at critical radius. Critical free energy occurs at critical radius or steric. This delta G steric corresponds to an activation free energy, which is the free energy required for the formation of stable nucleus. Eventually it may be considered as an energy barrier to the nucleation progress, because r steric and delta G steric appear at the maximum on the free energy radius. If we look at this plot, r steric and delta G steric are maximum. So we will derive the relationship for the r steric and delta G steric individually. Activation free energy, first we will discuss from the previous plot. The activation free energy is the delta G steric. It occurs at the critical radius r steric. And consequently at maximum of the curve in figure 10.2b, like we have already discussed this. This delta G steric corresponds to an activation free energy. This is a free energy required for the formation of stable nucleus. Eventually it may be considered an energy barrier to the nucleation process. Derivation for critical radius r steric is r steric and delta G steric appears at the maximum of the free energy. Derivation of expression for these two parameters is a simple matter For R steric, we differentiate delta G equation, which is equation number 10.1 with respect to R. If we differentiate the delta G equation with respect to R, remind that delta G equation, delta G equation is the summation of 4 by 3 pi r cube delta GV plus 4 pi r square gamma. If we differentiate with respect to R, so it resulting in and if we make it equal to 0, then solve for R is equal to R steric, then this will be 4 by 3 pi r cube delta G will be, this is the derivation of 3 r cube, the derivation of r cube is 3r square, while the derivation of with respect to dr and derivation of r square is 2r, and then make it equal to 0. After solving this equation, we will get the relationship for the critical radius. R is equal to R steric is equal to minus 2 gamma over delta G V. This is the equation for critical radius of a stable solid particles nucleus for homogeneous nucleation, and it is represented as equation 10.3. Later on we will use this equation 10.3 for the derivation of delta G steric critical energy. Activation free energy required for the formation of stable nucleus. How can we get the activation free energy? The expression for the activation free energy: substitute the expression for R steric into equation 10.1, yields the expression for the delta G steric. Delta G steric is equation 10.4. If we put the value of R steric, like we have derived this, the value of R steric, which is equal to 2 gamma over 2 gamma over delta GV, we will get the expression for the delta G steric, which is activation free energy required for the formation of stable nucleus. This is equal to 16 pi gamma cube over 3 delta GV square. This volume free energy change delta GV is the driving force for the solidification transformation, and its magnitude is a function of temperature. At the equilibrium solidification temperature Tm, m is the subscript, the value of delta G steric is 0. Delta GV is 0. Over here it is the delta GV. At the equilibrium solidification temperature Tm, the value of delta GV is 0. And with the diminishing temperature, its value becomes increasingly more negative. Delta GV is a function of temperature. This is the delta GV is a function of temperature, which is equal to delta HF times Tm minus T over Tm, where delta HF is the latent heat fusion, that is heat given up during solidification. Tm and T are temperature in Kelvin. In this plot, this is the schematic free energy versus embryo nucleus radius curves for two different temperatures. The critical free energy change delta G steric and the critical nucleus is R steric are indicated for each temperature. At T1, the red plot, the critical free energy is greater than the critical free energy at T2. If we look at the temperature ranges, T2 is mentioned that T2 is less than T1. For temperature less than, for the blue curve is the plot for the temperature T2, which is less than T1. The activation free energy, critical activation free energy, is less than. Similarly, the critical radius, the critical nucleus radius is also less than the critical nucleus radius at higher temperature. So we can conclude that for higher temperature, the activation energy, free critical activation energy, is greater than the critical activation energy at lower temperature. Dependence of critical radius on surface free energy, latent heat of fusion, melting temperature, and transformation. For getting the expression for the critical radius, which depends upon the latent heat energy delta HF and temperature, we substitute the expression for delta GV into equation 10.3 and 10.4. We will get R steric. This is the expression for the another expression for critical radius, which depends upon the temperature and the latent heat fusion delta HF. Latent heat fusion is delta HF, T is the temperature, Tm is the melting temperature, and the transformation. This is the critical free energy dependence upon the melting temperature and latent heat of fusion. Thus, from these two equations, both the critical radius R and the activation free energy delta G steric decreases as temperature T decreases, because these are in the denominator. The two equations, both the critical radius R and the delta G decreases as the temperature T decreases. We have explained this with the plot figure 10.3. schematic plots are given. Then the HF parameters in these expressions are relatively insensitive to temperature changes. Explain it further. The gamma and delta HF form. The gamma and delta HF parameters in these expressions are relatively insensitive to temperature changes. Gamma is this one and delta HF is this one. This is figure 10.3, where we want to discuss this with respect to the given equations. This figure 10.3 shows the curves for two different temperatures illustrate these relationships. Physically, this means that with lowering of temperature at temperature below the equilibrium solidification temperature Tm, nucleation occurs more rapidly. Nucleation occurs more rapidly. This is T2 is lower than T1. Nucleation occurs. Furthermore, the number of stable nuclei N steric having radii greater than R steric is a function of temperature, as N steric is equal to K1 exponential delta G over minus K or KT, whereas K1 is related to the total number of nuclei solid phase. We have already explained the exponential behavior of this equation in steric k1 exponential minus delta gv, that the exponential term of this expression changes in temperature have a greater effect on the magnitude of the critical internal energy delta G steric over here, which is a term then in the denominator, then the temperature T term in the denominator. The temperature term is delta G has more effect. Why? Because the temperature is lower. When temperature is lower below Tm, the exponential term in this equation also decreases, such that the magnitude of n steric increases. This temperature dependence n steric versus T will be explained further in the schematic plot. Here n steric versus temperature, the plots are shown in these figures, and 10.4a, the plot for the n steric, number of stable nuclei and temperature. This is the exponential term which is decreasing below that line Tm line until the temperature, when the temperature T2 is less than Tm. Another important temperature dependent step is involved in and also influences the nucleation. The clustering of atoms by short range diffusion during the formation of nuclei, the influence of temperature on the rate of diffusion. I think this diagram is necessary to explain the relationship between the number of stable nuclei and temperature. Here we explain one example. This is an example is about the computation of a critical nucleus radius and activation free energy. For the solidification of pure gold, calculate the critical radius r and activation free energy delta G steric if nucleation is homogeneous. Values for the latent heat of fusion and surface free energy are minus 1.16 and to 10 raised to the power 9. This is 9 is in the substrate times joule per cubic meter and 0.132 joule per square meter respectively. Use the supercooling value found in the table 10.1. This value will be given if this question comes in exam. Now calculate the number of atoms found in a nucleus of critical size. Assume a lattice parameter of 0.413 nanometer for solid gold and its melting temperature. Solution. In order to compute the critical radius, we employ equation 10.6 because delta HF is given. The equation, this is the equation 10.6. When Tm and delta HF is given, we have derived this equation using the melting temperature of 1064 degrees centigrade for gold, assuming a supercooling value of 230 degrees centigrade, which is taken from table 10.1. This will be given if this question comes in exam, and realizing that delta HF is negative. So compute these values. While we compute these values, we get the critical radius is 1.32 nanometer. For computation of activation free energy equation 10.7 is employed. Thus, delta G steric is this one, the expression. Put the values in this equation. And part B, in order to compute the number of atoms in a nucleus of critical size, assuming a spherical nucleus of radius r steric, it is first necessary to determine the number of unit cells, which we then multiply by the number of atoms per unit cell. The number of unit cells found in this critical nucleus is just the ratio of the critical nucleus and unit volumes. For the gold haze FCC structure, so here we provide the summary of the previous topics because we want to end this chapter. The homogeneous nuclei we have studied so far, the homogeneous nucleation and energy effects. We have explained this plot already, but we want to further, because of this importance, we want to explain it further. We want to summarize the effect of energy and how homogeneous nucleation is formed. This is the in this plots there is one red dotted line which represents the equation for the delta G is equal to 4 pi r square gamma, where gamma is the surface tension and surface free energy destabilize the nuclei. It takes the energy to make an interface. It is exponentially increases with the square of the radius of nucleation. Vertically, it represents the free energy delta G. Horizontally, in horizontal axis, the radius, the nucleus radius r is given. Here we study the effect of radius of the nucleus on the nucleation energy, due to the free energy change of the free energy. Delta GT is the total free energy, which is the summation of the delta Gs plus delta Gv, which we have already discussed, where delta Gs is 4 pi r square gamma and delta Gv is 4 by 3 pi r cube times delta Gv. It is volume bulk free energy delta Gv. Total energy is the sum of the surface free energy plus volume bulk free energy. So below this one, delta Gv is the effect. The blue line is the effect of volume bulk free energy, which varies with the cubic radius of the nuclei, while the green line is the sum of the effect of the energy over the nucleus radius. It is delta GT. We have already discussed this one. If we look at the middle, we can see delta G steric, and we see the peak of the energy. The energy increases from 0 to the peak to the critical. We call it a critical radius or steric, and at this critical radius we get the critical total energy. We can further explain the volume bulk free energy delta Gv which is equal to the volume free energy over the unit volume. R steric is critical nucleus. For R is less than R steric, the nuclei shrink. For R is greater than R steric, the nuclei grow to reduce energy. Solidification. We have already explained this formula. R steric is equal to minus 2 gamma times Tm over delta HF times delta T. Over here R is the critical radius, gamma is the surface free energy, Tm is the melting temperature. We have solved the above example for the Tm melting temperature when the substance was gold. Delta HF is the latent heat of solidification fusion. Delta T is Tm minus T. We call it supercooling. We have already explained the effect of supercooling over homogeneous transformation. Note that delta HF and gamma are weakly dependent on the delta T. The critical radius or steric decreases as delta T increases because these are an inverse effect. For typical delta T, R steric is nearly equal to 10 nanometer. For heterogeneous nucleation, we don't want to go in detail. It will be deviation from your scope of study, but if we compare that with homogeneous nucleation, for homogeneous nucleation requires a supercooling between 0.1 to between 80 degrees centigrade to 300 degrees centigrade, while heterogeneous nucleation occurs at slight supercooling between the range of temperature from 0.1 to 10 degrees centigrade. These form at structural inhomogeneities. The examples are container surfaces, impurities, grain bodies, and dislocation. So with this, we end up your course, and I hope that you make it. You prepare these few topics for your exam.